In this example, this is a two-dimensional example, we have two loudspeakers. They're separated by 2 meters, and they emit a 700 hertz tone in phase. A listener stands 5 meters in front of one of the speakers, but 2 meters to the side of center. We know the speed of sound in the room, and does the person hear loud sound or no sound? So first off, let's see what it's telling us about the geometry. So for the location of our person, 5 meters in front of the loudspeakers. So if I draw a line up here, then from here to here is 5 meters. Okay, so there's one position. And 2 meters to one side of center, if I draw a line representing center, then the person is 2 meters this way. And then the speakers themselves are 2 meters apart. Okay, there's what we have. The question is, does the person hear a loud sound or no sound? So how are we going to approach this problem? We know that loud sound is constructive interference, and we know that no sound is destructive interference. So we interpret that we have to find, is it constructive or destructive? In order to find that, we have to find delta phi. We have to find the phase difference from the two speakers. If the phase difference is an even multiple of pi, it's constructive and the sound is loud. If it's an odd multiple of pi, it's destructive and there's no sound. So this is where we're going with this problem. We know we want to find delta phi, so let's write down the equation for delta phi. So the equation for delta phi, the phase difference, delta phi is the phase difference of sound between the two waves from each speaker, is 2 pi over lambda times delta r. We use delta r instead of delta x because this is a two-dimensional picture, plus delta phi naught. This is the expression that's going to let us calculate the phase difference. After we see what the phase difference is, we can decide if it's constructive or destructive. What do we know that we can put in here? We know we need to put in the wavelength. So we might ask if we know the wavelength, and I would say we don't know the wavelength, but we do know the frequency and we do know the speed. So frequency equals 700 hertz, and wave speed equals 341 meters per second. We know that speed is frequency times wavelength, so wavelength is speed over frequency. 341 meters per second divided by 700 hertz gives us a wavelength of 0.4871 meters. With these kinds of problems, sometimes we get into trouble with rounding, so let's try and round as little as possible, at least in the beginning of the problem. Delta R stands for our path length difference. So delta R is the difference between R2 and R1. Here's where the problems tend to get a little bit tangly. It's identifying R2 and R1. So the first thing we'll do is let's label our speakers. So let's call the closer speaker, speaker number 1. And let's call the more distant speaker, speaker number 2. So just like x1 was the horizontal distance between the person and the speaker, now R1 is the distance between the person and speaker 1. Okay, so x was the distance between the person and the speaker, now r is the distance between the person and the speaker. For speaker 1, here's speaker 1, here's the person. So from here to here is R1. Let's see if we can find R1. Well, we know that this distance horizontally is 5 meters. This distance right here we can also find. So we got to do some geometry here. Here to here is 2 meters. Here to here is 1 meter. So this goes from the midpoint up the midpoint to either speaker is 1 meter. So if this is 1 meter, this is 2 meters, then this must be 1 meter. So my distance R1 then, it's the hypotenuse of a right angle triangle which has legs of 5 meters and 1 meter. So R1 is the square root of 5 meters squared plus 1 meter squared. It's going to be the square root of 26 meters squared, 5.099 meters. Again, keeping an extra significant digit here just because we can get into rounding troubles. Okay, that takes care of R1 to put in my path difference. R2 for my path difference. R2 is the distance from speaker 2 to the person. Okay, so I'm going to draw on top of my picture here. I'll try not to clutter it up too much. So from here to my person, this is R2. My distance from here to here, my horizontal distance, is still 5 meters. My vertical distance from here to here, this distance is 2 meters, this distance is 1 meter, so this distance is 3 meters. So then R2 is the square root of 5 meters squared plus 3 meters squared. And that turns out to be 5.831 meters. So path difference is how much further away is this speaker compared to this speaker. So we need to find this distance by using a right angle triangle. We have to find this distance by using a right angle triangle. And then we get our path difference by subtracting those two numbers. That's the hardest part of these whole series of problems. So we get 5.831 meters, subtract 5.099 meters, to get a path difference of 0.732 meters. There's my path difference. The last thing in my expression I need is delta phi naught. Delta phi naught, let's see, where are we going to find that out? It says it emits the tone in phase. So if things are in phase, then delta phi naught is equal to 0. So let's put all of these things up here. Delta phi equals 2 pi over lambda. Lambda is 0.4871 times delta r, which was 0.732, plus 0, our delta phi naught. 0.732 divided by 0.4871, that's 1.5. And if we have 1.5 times 2 pi, that equals 3 pi. So we see that our phase difference is 3 times pi. 3 pi is destructive interference. If it's destructive interference, it means that the person will hear no sound or quiet sound. So that's part A of the problem. Part B asks, how would this change if the speakers emitted sound out of phase? So what if it were out of phase instead of in phase? So if the sound were emitted out of phase, then the change to our problem would be, instead of delta phi naught equals 0, then delta phi naught would be equal to pi. So then our phase difference, delta phi, would be 2 pi for 0.732 over 0.4871. I left out my meters up above. There, better. plus pi equals 3 pi plus pi equals 4 pi. 4 pi is an even multiple of pi, so this would be constructive or loud sound. Okay, so that's a fairly typical kind of example. I will put in a couple of other extra examples in case you want more practice. People can't seem to get enough of this stuff.